जी, अस्सलाम वालेकुम। हेलो। हेलो, टेस्टिंग। जी सर, आवाज़ आपके पास ठीक आ रही है? लेवल ठीक है? अभी बढ़ाना नहीं कुछ भी, ठीक है? ओके।
सबको बताना. We will start our session of seminar at 10:30. Bismillahirrahmanirrahim. Ladies and gentlemen, Assalamu alaikum and good morning. I am Asma Batul from Department of Computer Science and Information Technology, Virtual University of Pakistan. It is requested to please switch off your mobile phones. The audience is requested to please rise for national anthem. I would like to invite Hafiz Muhammad Azim Sarwar to recite few verses from Holy Quran.
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم لا أقسم بيوم القيامة ولا أقسم بالنفس اللوامة أيحسب الإنسان أن لن نجمع عظامه بلى قادرين على أن نسوي بنانه بل يريد الإنسان ليفجر أمامه يسأل أيان يوم القيامة صدق الله العظيم.
Jazakallah. Ladies and gentlemen, I warmly welcome you all on behalf of Professional Development Center and the Department of Computer Science and Information Technology, Virtual University of Pakistan, in 3 days seminars on HPC, ANN, and data visualization. We are honored to have with us today our rector, Professor Dr. Arshad Salim Bhatti, in this session. Thank you, sir. I welcome the Director ICT, Mr. S.N. Puri, Virtual University of Pakistan, Head Department of Computer Science, Dr. Nasir Naveed, and our valuable participants from Computer Science and Information Technology Department. I welcome our guest speaker, Dr. Farooq Alawi. He has done his PhD in the field of physics theoretical from Queen Mary University of London, UK. He is the member of Association of Computing Machinery, ACM, Institution of Electrical and Electronics Engineer, IEEE, and Institute of Physics, UK, chartered physicist. He worked as different universities of UK on different posts as lecturer, sessional lecturer, and program leader. He has numerous postgraduate certificates from UK and Canada. He is a postdoctoral researcher with an area of interest in data science and neural network domain. He is currently working as CEO, Quantorain Enterprise Inc. This 3-day seminar systematically designed to target the undergraduate, postgraduate, and faculty members in each day's talk. In a talk with professional faculty members as in depth in the domain of high performance computing, applications and case studies will be discussed. The talk of postgraduate will enable the participants to give an understanding, usage, and importance of artificial neural networks in current era and in future. In an undergraduate talk, the participants will be enabled to learn about the basics of data visualization, its origin, and relevant information. Now I invite the worthy rector, Professor Dr. Arshad Salim Bhatti, for opening remarks. Please, sir.
बिस्मिल्लाहिर्रहमानिर्रहीम, अस्सलाम वालेकुम एंड गुड मॉर्निंग। अभी मैंने वैसे तकरीर तो कर दी है, आई एम सॉरी अगर किसी को बुरी लगी है, लेकिन आई एम रियली वेरी हैप्पी एंड थैंकफुल टू डॉक्टर फरख हलावी। अब आप सोचें, ही वाज फॉर रीजंस वो बाहर नहीं आ सके, सिंस ही हैड कमिटेड दीज 3 days, ही टुक जर्नी फ्रॉम कराची टू लाहौर बाय बस। ठीक है, ये इनकी कमिटमेंट का लेवल देखें, और इनको जवाब आप दे सकते हैं अपनी एंथुजियास्टिक पार्टिसिपेशन के साथ। इनको भी मजा आया कि हाँ मैं वर्चुअल यूनिवर्सिटी आया था, एंड देयर फैकल्टी वाज वेरी लाइवली, और उन्होंने मेरे साथ डिस्कशन की है, एंड वी हैव कम अप विद सम आइडियाज इनके पास भी बहुत होंगे, आइडियाज आपके पास भी बहुत होंगे। यू हैव टू रेजोनेट आइडियाज, या कोई ऐसा आइडिया जो इनके पास नहीं है जो आप दें और ये उससे एक्साइट हों। लेट्स वर्क टुगेदर, ये पर्पस है हमारे पास। ठीक है, लुक एट दैट 3 versatile topics, different topics: high performance computing, artificial neural networks, and then data visualization. तो आजकल ना, कल 2-3 दिन के लिए आई वाज इन वो HEC की वो VC's कॉन्फ्रेंस पे थे। कल देयर वाज अ प्रेजेंटेशन बाय पाशा एंड बाय PSEB, उनको 10-10, 15-15 मिनट दिए गए, एंड बोथ फॉर लिटरली क्राइंग कि हमारे ग्रेजुएट्स हैं, उनके पास ये स्किल्स होनी चाहिए और ये स्किल्स नहीं है, एंड वी नीड 40,000 पीपल फॉर एम्प्लॉयमेंट। वो जो फ्रीलांसिंग के 8-10 एरियाज हैं ना, जिसमें वेब कंटेंट से लेके एप्लीकेशन से लेके, खा वो एप्पल की हों या वो एंड्रॉयड की हों, और अभी उन्होंने डाटा एनालिटिक्स को नहीं देखा। डॉक्टर साहब विल टेल यू कि दिस इज द वन वेयर you need programming skill, but you need to show कि डाटा का रिस्पॉन्स क्या है, डाटा को अंडरस्टैंड कर सकते हैं, उससे ट्रेंड निकाल सकते हैं। डाटा जो हमने वर्कशॉप की है पिछले हफ्ते डाटा एनालिटिक्स की, पीपल नीड, बैंक्स नीड्स, स्टॉक एक्सचेंजेस नीड्स, इवन हायर फिजिक्स या जहाँ एक्सपेरिमेंट्स हो रहे हैं वहाँ पे भी डाटा एनालिटिक्स के लोग चाहिए, because in each experiment they produce trillions of bytes of data सिर्फ एक collision के अंदर। तो एक बात जो मैं कहूँ, I'm very thankful, डॉक्टर फरख हलावी के साथ मेरा तारुफ बहुत पुराना है, and then we got lost but we have a very common friend। उन्होंने मुझे दोबारा याद कराया, and luckily last month we were in Karachi, 2 months almost, हाँ 1 महीना हो गया, मैं और पुरी साहब कराची में थे, and he turned up। मेरे एक दोस्त ने कहा कि आपको एक सरप्राइज देता हूँ, and I saw him, I thought you were in Canada or in UK, नहीं I'm in Karachi for last few weeks or a month। तो उसी वक्त हमने डिसाइड किया let's come to लाहौर और हमें अपनी एक्सपर्टी से फ़ायदा दें। इन्होंने आज से 15 साल पहले हाई PC HPC की एक प्रपोजल गवर्नमेंट ऑफ पाकिस्तान को तैयार करके दी थी, अनफॉर्चुनेटली वो चली नहीं थी, and we are still hoping कि we would do something on that इसके ऊपर। लेकिन एक चीज़ मैं बता दूँ, जिस एरिया में इन्होंने PhD की ना फिजिक्स की, that is high energy physics। ठीक है, खा थ्योरेटिकल करें खा एक्सपेरिमेंटल करें, But high energy physics is the one area where I believe मैं उस एरिया में PhD नहीं की, लेकिन मुझे आखिरी अभी ये वर्चुअल यूनिवर्सिटी में आने से पहले 5-6 साल मुझे उस एरिया में काम करना पड़ा. The 3 characteristics that student gets: he's a good physicist, he becomes a very good computer scientist क्योंकि उसने डाटा को हैंडल करना है और उसको एल्गोरिदम डेवलप करने पड़ते हैं, उसको कंप्यूटर साइंस आती है और एल्गोरिदम डेवलप करता है मशीन है कौन सी है उसके पास. जब तक कि उसको मशीन की इनसाइड का नहीं पता होगा ना, वो एल्गोरिदम नहीं डेवलप कर सकता. सो उसको डिस्ट्रीब्यूटेड कंप्यूटिंग भी आती है एंड ही नीड्स हाई परफॉर्मेंस कंप्यूटिंग. एंड थर्ड इज इलेक्ट्रिकल इंजीनियरिंग. जब तक कि उसको डिटेक्टर की इलेक्ट्रॉनिक्स नहीं पता होगी ना, इट्स नॉट ए सिंगल डिटेक्टर. हमारे पास ना ये मोबाइल फोन में ना देयर इज वन डिटेक्टर. पता है ना कौन सा डिटेक्टर है? कोई बता सकता है इस मोबाइल फोन में डिटेक्टर कहाँ पे लगा हुआ है? 2 डिटेक्टर हैं एक्चुअली. एक एंटेना है, वो भी मैं कहता हूँ डिटेक्टर. बट देन दिस फोन इन देयर, अपना कैमरा, दैट इज डिटेक्टर जो तस्वीरें खींचता है. दिस इज सिंगल है. बट हाई एनर्जी फिजिक्स में जो डिटेक्टर इस्तेमाल होते हैं ना, देयर आर लाइक 10 लेयर्स ऑफ डिटेक्टर्स, डिफरेंट लेयर्स. कहीं में 12 लगी हुई हैं, कहीं पे 16 लगी हुई हैं. हर डिटेक्टर डिफरेंट एनर्जी के ऊपर पार्टिकल्स को डिटेक्ट करता है, डिफरेंट टाइम्स के ऊपर डिटेक्ट करता है. इनको अगर डिटेक्टर की परफॉर्मेंस नहीं पता होगी ना, ये सिग्नल को अलग नहीं कर सकते, ये उसमें से डाटा एक्सट्रैक्ट नहीं कर सकते. सो एनी पर्सन हु हैज डन अ PhD इन हाई एनर्जी फिजिक्स इज अ वंडरफुल कंप्यूटर साइंटिस्ट. वो आपको याद है डॉक्टर अली अमर सैयद आए थे, ही वाज हाई एनर्जी फिजिसिस्ट. और उसकी स्किल जो सी है सारी एल्गोरिथम डेवलपमेंट में इसने फिलिप्स ने इस्तेमाल की है. अब वो सिस्टम आर्किटेक्ट के तौर पर फिलिप्स वालों ने हायर किया हुआ है. PhD के साथ कोई ताल्लुक नहीं, बट इट्स द स्किल विच ही लर्न ड्यूरिंग हिज PhD. सो फिजिसिस्ट, कंप्यूटर साइंटिस्ट एंड देन एन इलेक्ट्रिकल इंजीनियर, ये 3 उसके एट्रीब्यूट्स बनते हैं. एंड ही और शी कैन गो इन एनी डायरेक्शन. कंप्यूटर साइंस हैज बिकम अ स्किल रादर देन अ डिसिप्लिन. एक स्किल है जो मैं कहता हूं कि हर बच्चे को आनी चाहिए. प्रोग्रामिंग इज लाइक हैविंग ए कैलकुलेटर इन योर बैग, और कैलकुलेटर को इस्तेमाल करना आना बहुत जरूरी है. ठीक है. वो सर फ्यू इयर्स अगो थाईलैंड की एक यूनिवर्सिटी ने कहा था कि उन्होंने दे स्टार्टेड अ प्रोजेक्ट, एनीवन हु हैड अ स्मार्टफोन एंड एज अ स्टूडेंट वो यूनिवर्सिटी में रजिस्टर करता था और वो उसके फ्री टाइम में यूनिवर्सिटी उसको कंप्यूटिंग के लिए इस्तेमाल करती थी और यूज टू पे टू द स्टूडेंट. हफ्ते में 4 घंटे हमने तुम्हारा इस्तेमाल किया, दिस इज द मनी यू आर गोइंग टू गेट. ये लोग यहाँ, एंड दिस इज डिस्ट्रीब्यूटेड कंप्यूटिंग. और कंप्यूटर साइंस डिपार्टमेंट ये काम कर रहा था कि हम उन बच्चों के स्मार्टफोन्स का यूज करें टू डू कंप्यूटेशन. तो ये जौन सा, प्लीज माई रिक्वेस्ट टू यू इज टेक फुल एडवांटेज इनके यहाँ पे आने का. आई विल बी वेरी हैप्पी कि मेरे पास बाद में बच्चे आए कि जी हमने इनके साथ ये प्रोजेक्ट डेवलप किया है एंड वी वांट टू डू दिस प्रोजेक्ट, और वो उसको वेरीफाई करें हाँ ये है. एंड यूनिवर्सिटी विल गिव यू ऑल द सपोर्ट टू कंटिन्यू. सो इट्स नॉट लाइक, देखिए यूनिवर्सिटी का मेन काम है नॉलेज क्रिएट करना. डिसिमिनेट तो कर ही रहे हैं आप, डिस्ट्रीब्यूट तो कर ही रहे हैं, बट द क्रिएशन ऑफ नॉलेज इज ऑल्सो ए जॉब. और जितनी अच्छी एनवायरनमेंट मेरे ख्याल में वर्चुअल यूनिवर्सिटी के पास है टू डू दैट जॉब, वो किसी और यूनिवर्सिटी में नहीं है. ये मैं आपको बता रहा हूँ, ये वर्क इन मैनी यूनिवर्सिटीज और पाकिस्तान में ये हाल है. ठीक है, आई विल स्टॉप हियर. थैंक यू वेरी मच. थैंक्स टू नासिर, इन्होंने इतने छोटे टाइम में ये सारा अरेंज किया. टू पूरी साहब हु गिव फुल सपोर्ट एंड ही इज वेरी apprehensive and taking this one and then delivering it, इसको डिलीवर करने के ऊपर भी. और आपने देखा होगा प्रोफेशनल डेवलपमेंट सेंटर, ये एक्टिविटीज़ अब हम एक प्लेटफॉर्म से करना चाह रहे हैं जिसको हेड पूरी साहब कर रहे हैं, सो दैट के पूरे पाकिस्तान में इनकी एक्टिविटीज़ जाएंगे. हम अब वैल्यू एडिशन अपनी फैकल्टी में अपने स्टूडेंट्स में थ्रू दिस प्लेटफॉर्म कर सकते हैं और कर रहे हैं. और दिस एक्टिविटी विल गो इनटू हिज इन द प्रोफेशनल डेवलपमेंट सेंटर एंड डिपार्टमेंट्स जो उनसे वो सुजेस्ट करें, उनको कोलैबोरेट करें उनके साथ और एक्टिविटीज़ करने के लिए इस तरह की जिसमें कि हम वैल्यू एडिशन करें. एक चीज़ जो मैं देख रहा था कि आई डोंट नो बट नेक्स्ट टाइम या कल या परसों के लिए भी एडवर्टाइज इट ऑन पर्न एज वेल. सी स्टूडेंट और फैकल्टी फ्रॉम अदर यूनिवर्सिटीज दे कैन जॉइन अस, दे शुड जॉइन अस. ठीक है, तो आज का अगर तो लेट हो गया, लेकिन कल का और परसों का आप जरूर कर दें. there may be people who would like to listen to Dr. Farag साहब. ठीक है, चलें. Thank you sir, thank you very much आप लोगों का और टीवी की टीम का, टेक्निकल टीम का, एडमिनिस्ट्रेशन का, सबका बहुत बहुत शुक्रिया. और सर अगर कोई कमी रह गई हो ना तो आई एम रिस्पॉन्सिबल फॉर दैट बीइंग द हेड ऑफ द ऑर्गेनाइजेशन. थैंक यू वेरी मच, शुक्रिया.
Thank you very much, sir. Now I invite Honorable Guest Speaker, Dr. Farooq Alawi, for his talk. This is the on. And then next.
ठीक है, इसमें लेजर नहीं.
So laser light है. इसी को जब
ओके
on-
ठीक है, गॉट इट. ठीक है. बिस्मिल्लाहिर्रहमानिर्रहीम. रब्बि इश्रह ली सदरी व यस्सिर ली अमरी वहलुल उक़दतम मिन लिसानी यफ़क़हू क़ौली. अस्सलामु अलैकुम. And I'd like to thank the faculty members and director personally for inviting me here. A lot of hard work went into arranging this seminar, and hopefully, we'll all benefit from the results of it, inshallah. So once again, assalamu alaikum. It's nice to be able to say assalamu alaikum to a class. Where I come from, you never think about something like this, but at least in this country you can do this. So just to follow on from what Batisab said, data science. The three topics which we selected for these 3 days have a common theme, and that common theme is data science. And why is that? Data science has been called the new oil. The size of the oil industry, it's a multi-trillion-dollar industry, and data science is heading that way if it isn't there already. One of the best professional careers any student can embark on these days is a data scientist. In Canada, where I was before I came here, people are getting salaries of $100,000 plus simply because they're able to do a bit of statistics and they know how to program statistical calculations. So that's something for you guys to think about, inshallah. Okay, I want to make it clear that this is not a lecture. This is a discussion seminar, and I hope to be completely open in terms of interacting with everybody. Feel free to stop me anytime and ask me anything. And it's not just you learning from me. I hope to learn from you as well. Inshallah. Okay. So this is an outline of the talk. I broke this up into 5 sections. First of all, we'll talk about motivation. Why do we need HPC? HPC, of course, is high performance computing. There has to be a reason for everything, and even high performance computing needs a reason to exist as a separate discipline. Then we look at hardware because my background happens to be hardware. So we discuss hardware, the side of things of high performance computing architectures. Why does architecture matter? Then we look at the so-called eternal battle. Computation and communications are 2 separate industries which actually started off from the same laboratory, as I will discuss later on. Then they took separate paths. And then about a couple of decades ago, they started to converge again. But you still have this conflict between them, that computation and communications seem to clash. And one of the key things which actually hampers or restricts high performance computing from performing in the best possible way is the communication bottleneck. And what can we do about this? Then look at software. Now, I'm not a software guy, but I will discuss the software side of things. High performance computing, you're building all this wonderful hardware, which is highly capable. How do you program these things? How easy is it to program them? And then finally, we look at application case studies. So this is a completely open discussion. I have some news items to share with you, a couple of videos which are very, very informative. So I'll play those. And we hope to finalize this talk with a discussion on what we can do in Pakistan to build up a high performance computing culture here. As Professor Saab said, we tried to do this about 15 years ago. It went nowhere. Maybe this time we'll be lucky, inshallah. Okay, so let's start. So first of all, I just want to show of hands here. How many computer scientists do we have here? Okay, half the class. Any hardware engineers? Just one? Right. Any physicists? Physicists, of course. Chemists? No. Biologists? No. Artists? No. No, there isn't. Okay. There's a reason why I'm asking this question. And it's to do with this thing, this word here. Whoops. Disciplinarity, which basically means the subject area, which is your area of expertise. Okay, so what is your field of academic study is basically an answer to the question, what is your disciplinarity? And we find that increasingly people are multidisciplinary, right? You don't have to be, as Dr. Saab said, you come from a physics background doesn't mean that you automatically cannot do computing, or you come from computing and you cannot do electrical engineering. So you have to have these multiple skills these days, and it's part and parcel these days of being a graduate. And especially if you're going out in the workforce, employers love people like that. Oh, you can do X, you can do Y, you can do Z. Fantastic, they'll hire you. All right. So when you look at disciplinarity, it's become a subject in its own right. Okay, so we have something called interdisciplinarity, which is basically take a subject, and within that subject you have subfields, and you're able to cope with the multitude of them. So that's known as the interdisciplinarity. Then you have multi, where you have different disciplines working together. For instance, physics and computer science working together, right? So that's multidisciplinary. Then we have cross-disciplinarity, which basically one discipline views another from a completely different perspective. Very good example. I talked about artists. Any artists here? Obviously there isn't, but artists use computers these days, right? And equally, computer science is now influenced by art. There are entire subject areas to do with the graphical user design and user experience, and the artist has a significant part to play in this. Okay, so that's a great example of being the cross-disciplinary. Then we have inter, where you integrate knowledge from another. Okay, so bioinformatics, perfect example of this, which basically using a lot of statistical and mathematical models, computational models to develop solutions for biological problems. And then we have this thing called trans, where you unite entire frameworks. All right, and high performance computing basically is a transdisciplinary subject, and it should become clear to you by the end of this talk why that is so. All right, because we are combining frameworks from electrical engineering, from computer science, from a whole bunch of other things as well. Okay, all right, so the first reason, disciplinarity, basically it tells you how high performance computing exists, not as a subject in its own right, but as a subject which has multiple angles and multiple viewpoints from all these other subjects, and it's a transdisciplinary subject. All right. Now, so from how we come to why do we need HSPC? Well, first of all, it's to do with time. Time is recognized as our most valuable resource. There's a nice little book here. You can look this up for yourselves, and you can see that it's been called the most valuable resource. Now, does anybody know why this is called the most valuable resource? Any ideas? Why are there so many time management courses in management? Right? Think about that, right? Why is it that, they say, oh, once time is gone, gaya waqt wapas nahi aata kind of thing, how does that work, right? So you're only given one lifetime, and that lifetime is finite. It's not expendable. You cannot borrow time. You cannot sell it. You cannot store it. People say, I'm saving time. You're not saving time. No, you're simply using that time to do something else. Okay, so time is absolutely your most valuable resource, much more than money. Money, if you lose it, you can recover. If you lose time, you never get it back. All right. Why am I saying this? What's this got to do with computer science? Well, this is a philosophical angle. All right. So we'll see later on that one of the key factors, which is a motivator for us to build these high performance computers, because we are trying to save time. We are trying to solve difficult problems, large scale problems in as little time as possible. Right. And we do that because as a species, we have this intrinsic ability to recognize that, time is a valuable resource. We have to save it. Okay. All right. Next thing is human nature. What's human nature got to do with the high performance computing? Well, what kind of problems does high performance computing solve? Any ideas? If I gave you some supercomputer, you're not going to play a game with it, right? You're going to try and solve a problem, correct? Okay, well, can you think of some problems that you might want to solve with the high performance computer, supercomputer? Anybody? Correct, yeah. Yeah, okay, so that's an example. Okay, but the examples are many, right? Climate modeling to protein folding to nuclear physics, financial analysis, which involves data science, right? Designing drugs these days, medicines and whatnot. So all these things they require very, very high performance computers. And the more we learn about these about the nature around us, the more we want to find out more. And then it becomes even more imperative for us, build a machine, a computer, which can then help us to solve those extra problems, right? So one problem solution leads to another set of questions, and you try and solve that with even higher performing computers, and then and so on. It just goes on forever. So this is a very nice book, which if you get a chance, you should read it. It's written by Mario Livio. He's a physicist actually, but he's written a book about philosophy. Right? He's talking about curiosity. Why are humans curious? Well, I mean, what drives us to solve all these problems? The other animals don't do this. Okay. So again, this is an intrinsic human desire, right? We are curious by nature. And this book actually addresses this issue and tells and points out exactly, what is the reason for this curiosity, and why curiosity is in fact one of our survival instincts. If we weren't curious, we probably would have died out as a species long ago. Okay, so think about that. All right, and solve complex problems. So, so I've given you 4 reasons. There are many more we can think of, right? But hopefully this gives you an idea of why we need to solve, why we need to build high performance computers, and why they're useful. So of these reasons, 2 of them, the time and the human nature, right? These are philosophical reasons, but they're important, right? Because they help to guide us when we go and build and design these things. Okay, so we move on now to why does architecture matter? So let's understand the HP and HPC, right? So what do we mean by high performance in high performance computing? So first of all, in order to answer this question, let's step back a bit and look at the historical view of computing. All of high performance computing is a subset of computing itself, and computing has an absolutely fascinating history. Okay. Okay, so we have a history of computing which basically began as large mainframe size machines here. Okay, this particular link here, which I've given, you can look this up on your own. Basically, it goes through the invention of the very first mainframe computers in the 1940s, and takes you up all the way towards the 1960s, when computing was beginning to be an industry by itself. Okay, so during that era, which is, do you mind if I use another? Okay, so during this era, mainframes, which were large room-sized machines, they were used by universities and by government mostly, right? Okay, so these were the people with money, and they were building these machines in order to solve their particular sets of problems. Okay, so when they were successful, then during this era here, we found that from mainframes, people started developing minis, and these machines, the VAX and the PDP-11 class machines, became extremely successful. But what you also found was that corporations got interested as well. Okay, along with universities and governments. So corporations, they started attacking and solving large business problems. So the likes of MasterCard and Visa card company, they all came into existence around this time simply because the computing power was available to handle large customer accounts and stuff. Okay, then in the 1970s, the micros made an appearance. So Intel in 1971, they launched the 4004, which is the history's first microprocessor. It had only about 27,000 transistors, right? It was an 8-bit device. It ran at only a few kilohertz, but this was the start of the computing, desktop computing revolution. Okay, which led just about a decade later, it led to the IBM PC, which was launched in 1982, another Intel-based machine, 8086 processor, 8 bits. It came, I think, with the 16 kilobits of RAM, okay, and a big floppy drive and stuff. Okay, but that kicked off the entire microcomputer revolution, which today means that there's no computer, there's no desk on anybody's home or office which does not have a computer on it. Okay, all right. So these things move very fast. We find that 1982 the IBM PC came into being. Then within 7 years the web was invented by by this physicist working in CERN, and sorry about that. Okay, and he made it open source. The smart thing he did was he made it open source, and the result after that. Okay, at the same time, 1991, 2G GSM mobile networks came into being, right? So remember when we talked about computation and communication, right? Okay, we see that this was the era where these two industries started to converge towards each other. All right, because previous to this, although some mobile networks did exist, they were analog, they were not digital, so they did not mix in with computer science and computer hardware very well. But this changed the game, 1991. Okay, so this, for the first time, it was possible now to have mobile networks with some kind of data over the air. All right. So looking at this summary, what we find is that the definition of high performance changes with time. Okay, the definition of high performance in this era was these big mainframe machines, room-sized machines, right? That required a lot of cooling power and whatnot, and a lot of electricity to work. Okay, about 3 decades later, you had these machines which were high performance, and then the micros eventually they took over. They became high performance as well, right? You can solve very, very complex problems on today's desktops. All right. And of course, now, of course, everybody gives the example that, the Apollo rockets, which took command to the moon, had less computing power than your cell phone in your pocket today, right? Okay. Right. So, what do we mean by supercomputers? Now, supercomputers, I wish to distinguish this or separate this from high performance, because supercomputers are a special class of high performance computers for research and military purposes. Okay, all right. And the supercomputer industry was dominated for a long time by the US and Japan. Companies like IBM, Cray, CDC, etc. They used to build these machines and sell them to government, to corporates, etc., etc. Okay, and they used to have heavily customized CPUs. Now, I'm showing this slide because later on you'll see that this is no longer the case. Today, if you have enough resources, financial resources, you can actually use off-the-shelf CPUs to build a supercomputer which can beat any of these devices from a few decades ago. Okay, all right. Moving on to hardware. So I'm going to do a quick review of models of computation. So let's look at flow mechanisms, right? Because computing works on principles of flows. A set of instructions flows through the system and gives a set of results, right? So you have 3 kinds of flow mechanisms in all of computing, not just high performance. Okay, so you have either control flow machines or data flow machines and demand flow. So in this slide, I'm going to look at data flow machines. Data flow machines is basically an idea that computation happens when the data becomes available. So here's an example of some nodes. We've got 6 nodes here. You have an addition node multiplied by 4 node, another multiply node, a subtraction node, addition, and a divide node. Okay, and the output of these nodes, these are computational systems which perform very, very simple basic kind of computations, right? As soon as some kind of data becomes available, it will create a result. Okay, so that's data flow. All right, so when A and B have some non-zero value, you will find that some result appears here, and as long as there's a result here, then you find that this subtraction will take place and so on, and then the data will flow from the top and emerge here with the result that you want. All right, now let's look at demand flow. Demand flow is the opposite. It's basically bottom up. So if data flow was top down, from the top, the data appears and you get a result. Here is driven by the demand for a result. So if there is a demand for a result D, right, is going to force a set of inputs in here. And if there's a demand for some result here, it's going to force a set of inputs here, and so on, going back up. Okay, so that's known as the demand flow. So demand flow and data flow are opposites to each other. One happens because data becomes available. The other happens because the result is required and it forces the data to be available. Okay, and then finally, control flow. Now, control flow is basically the kind of computing models that we are normally familiar with. And what we have here is a general diagram, which basically shows you a CPU. Okay. So in the CPU consists of a control unit and an arithmetic and logical unit. Okay, and it is connected to a data memory. Okay, and what you have here is an address bus, which is unidirectional. It just goes one way, because what the CPU has to do is it has to find an address in this memory. Okay, get some information out and bring it in, do something with it, and put it back. So this is your data bus, which is bidirectional, right? And the kind of information that you find here is either instructions or data, or all right, and then. And then once the result is calculated, it's stored back into the data memory. Okay, so if you look at this part here, this is your classical von Neumann architecture machine, right? Von Neumann architecture is distinguished by something else, which is known as the Harvard architecture, right? So on the left-hand side, we have an instruction memory. Which can be read-only, right? So this the Harvard architecture basically says that the instruction memory is separate to the data memory. In a Harvard architecture machine, you would have two pieces of memory, one over here which only has the instructions, and then you would have a completely separate machine, separate memory system here which has only the data. Okay, so by keeping the data in the instructions separate, you actually boost performance, right? And the very first mainframe CPUs were actually Harvard machines, Harvard designed machine, not von Neumann machines. And it's a bit unfortunate that, when microprocessors were developed, they decided to save money essentially and go for this limited way of doing things rather than, saying, okay, let's put in some extra memory. But there's a reason for that. They were saving money simply because memory in those days when these things were designed was actually quite expensive. It was the most expensive part of the entire system. So it does make sense why they did it. But from a performance point of view, right, if we had to redesign the CPU from the ground up today, we would definitely go with the Harvard architecture, not the von Neumann architecture. Okay, so here's a quick review of stuff which anybody who's familiar with computer science should be familiar with. So Moore's law, named after Gordon Moore, founder of one of the co-founders of Intel, and basically it's not really a law. It was basically an observation. Because he was a physicist who started this company and in Intel, obviously, and he basically envisioned that there was a prediction from him that the transistor density count would double every 2 years, right? And did this prediction actually hold out? And the answer is yes, it did, because if you see from 1970 all the way up to 2020, right, you see what is pretty much a straight line. And here you have a logarithmic scale of the transistor count, basically doubling every 2 years, right? Now, this is not expected to last forever, right? Because remember, this is not a physical law. It's not some physics thing which is dictating this. It's just marketing and our ability to cram more and more transistors onto a piece of silicon. It's expected to end around 2025 in about 3 years' time. And what happens after that? Well, we don't know. But the demand for higher performance computing will continue beyond 2025, and they'll find a solution. Whether it's optical or going with some substance other than silicon, we don't know yet, but that's something for time to tell. Okay, another classification which should be familiar to anybody who studied computer science, Flynn's taxonomy from 1966. Basically, Michael Flynn was somebody who said that, look, if you're going to build these parallel machines, okay, then you have to look at how the instructions and the data interact with each other. Now, I'm mentioning parallel machines for the first time here. What is so special about parallelism? Any ideas? Same time, yeah. Okay. So why would we want to execute multiple instructions at the same time? It goes back to our philosophical slide. Yeah, to save time. Okay, so we try to save time. Okay, so again, as human beings, if we were good time managers, right, we would try and do 10 things at the same time. Of course, we can, but it would be nice if we could do that. So that's pretty much the philosophy that we've adopted when we go with parallel computers. We say that, look, we have this fixed time slot, we have to solve this problem, and the problem is going to take X number of steps. So instead of taking X number of steps, let's try and compress that into the limited time that we have and try and do X things in that one time. It's not always possible, but we do solve a lot of these problems, fortunately. Okay, so Flynn basically said that if you go with a single instruction acting on a single piece of data, you have what's known as an SISD machine, single instruction, single data stream machine. Example of that is a classical CPU, Intel, Motorola, whatever. Okay, but if you have a single instruction operating on a multiple data set, in other words, a vector, not a scalar value, right? Then you have what's known as a SIMD architecture, right? Single instruction, multiple data. Examples of that are vector processors and GPUs. Now, a vector processor is basically similar to a standard CPU, except that it deals with long vectors, right? It deals with the n-dimensional data sets in one go. And GPUs, graphical processing units, sometimes also known as general purpose units now, also perform on the same principle. Then you have these multiple instructions acting on a single data. Now, this actually, if you think about it, this doesn't make sense. Why would you want to have a single piece of data and have multiple instructions asking it to do different things? So not really for computer science, but it does have applications outside computer science. For instance, in fault-tolerant systems with redundancy. Okay, so if you want to have some safety mechanism, to guard a place or whatever, right? Okay, so and you have multiple instances of those. Then what you do is you make sure that each one of them is solving the same problem, but doing it at a different time or in a different way. So that's an example of having multiple instructions given to the same data set, right? And then finally, we have MIMD, multiple instructions acting on multiple data sets. Examples of them are general purpose GPUs and multi-core CPUs. So we'll see later on that, CPUs around the 1990s, in late 1990s, early 2000s, they started putting multiple cores on the same piece of silicon in order to increase the parallelism and hence the performance of CPUs. And there was a good reason for that. Okay, another thing which should be familiar to all computer scientists, Amdahl's law from 1967. So basically, this is a way of calculating what your speed up is if you decide to go from a sequential way of doing things to a parallel way of doing things. All right. So let's look at this set of assumptions which is required in order for Amdahl's law to hold. So you have a sequential application which requires so many units of time to execute on a single CPU. Right. So let's say it takes 5 seconds, t is equal to 5, for instance. All right. Then the application consists of some number alpha between 0 and 1, which can be parallelized, because not everything can be parallelized, right? There are dependencies always in the data sets which prevent parallelization, but some parts of it can be easily parallelizable. So maybe, X 9% or 10% or maybe 50, 60% if you're really lucky, can be parallelized. The other part, 1 minus alpha, cannot be parallelized, so it has to be done sequentially. And the parallel execution does not incur any communication overhead. Now, this is a very bold assumption because all parallel computation does in fact require some kind of communication. And remember what I said, that communication and computation are always in conflict with each other. So it's not a good assumption, but for the purposes of getting a handle on this, it is okay to make the assumption for now. All right. And the parallelizable parts can be divided along any number of CPUs. So the idea is this, that you have a problem, alpha percent of it can be parallelized, 1 minus alpha cannot be parallelized, and you have n number of CPUs, and you have t time in order to solve the problem. So what you do is you partition the problem, give it to the different CPUs, right, and let it do its job. What kind of speed up do you expect? Well, Amdahl calculated that the efficiency of this would be the speed up divided by n, where n is the number of processors. And the speed up is defined simply as the time of the sequential execution divided by the time of the parallel execution, right? Okay, the idea is that the parallel execution would be faster, right? So what you would end up with is a number greater than 1 for this ratio, the t equals, for the t sequential divided by the t parallel, right? And then when you play around with these numbers, you get this nice looking formula here. And if you take the limit of n going to infinity, in other words, the number of processes becomes very, very large, then what you see is that the speed up goes like 1 over 1 minus alpha. This would be a fantastic result if it held in practice. It doesn't. It doesn't. And the reason it doesn't is because, you know, two things are missing in this in this calculation. One is, of course, that you're ignoring the communication side completely. And the second thing is that you're looking at the whole problem from the perspective of the parallel process, not the sequential process. And it really is a sequential process which has an effect on how good your speed up is. Now, in these things, the speed up is actually calculated by actually performing a stopwatch calculation, right? So you look at the problem solved on a sequential processor, you set your stopwatch and see how long it takes. Then you do the same thing on a parallel one, set your stopwatch, and then you perform the comparison. Okay, now if Amdahl's law held perfectly, which it doesn't, right? This is the kind of speed up you might expect as the number of processes increased, okay? And this is what you would expect in terms of the efficiency. But in reality, this is what happens, right? This particular curve shows that, it just carries on forever and forever. It doesn't happen that way. In reality, what you find is that, it starts to saturate around here, right? So the more processing computing power you throw at the problem, the more the saturation kicks in, and the less is your return in terms of actually seeing any benefits. Okay, this is known as the law of diminishing returns. There comes a point where putting extra effort into the problem to try and get better results stops working. Okay, it happens in real life as well, by the way, right? It's not just computing. Okay. Right, now let's look at high performance through enforced parallelism. Where can we find opportunities to parallelize stuff in control flow code? Remember, we said that there are three types of flow, right? There's data flow, there's demand flow, and there's control flow. So control flow is the kind of computers that we work with, and basically it's a set of instructions. As a programmer, you give the computer a set of instructions, okay? And then as a hardware designer, you have to look at ways to parallelize that. So let's look at this this example here. This is basically a high-level language being used to code for the factorial function, right? Now, when you compile this, right, you end up with this assembly language code, which is still human readable, right? Okay, and then, before it gets executed, of course, it has to be converted to full binary. But the reason I've written it out like this is simply because, it's still human readable. Okay, so this is the perspective from the point of view of the programmer. The software engineer sees this. If he's a good software engineer, he will understand a bit of this as well. And he might be able to optimize bits here and there to get the best performance out, right? This is what happens when the program gets executed. So that's a view of the memory, right? As a programmer, you should know what's happening in memory, right? So things get calculated, they get stuffed into memory, stuff gets transferred between the CPU and the memory in your data bus, etc. Okay, and there really isn't much you can do here in terms of parallelization. Unless the problem itself was intrinsically parallel, you're stuck by the limiting features of this control flow architecture, right? Now look at what happens from the perspective of the hardware engineer. The hardware engineer does not see this. He may understand it, right? But he is interested in signals. What does he see? He sees that there's a fetch cycle, right? And this is your clock. This is your system clock, which is driving the entire process. Okay. Then there's a read cycle, and these are all the signals on the CPU. There's a whole bunch of them, of course, right? And there's a write cycle. All well and good. Can you do something and parallelize this just from the signals? Any ideas? No, you can. Just by looking at signals, you can. But if you're an architectural engineer, not just a design engineer, then there are opportunities. Okay, and this is an obvious way of exploiting that opportunity. parallelism via pipelining. Anybody who's a computer scientist will know what pipelining is. So basically the idea is this, that here's your system clock, which is driving the entire process. You have a bunch of instructions flowing from the top to the bottom, right? So each one of these instructions goes through n stages, depending on the design of the CPU, in order to be fully executed, right? So typically there are 5 stages, but there can be many more, okay? So you have an instruction fetch cycle, then instruction decode, instruction execute, there's a memory access, and there's a write back, okay? And there's usually a 6th one called the retire, where you clean up everything and just, move on to the next thing, okay? So the idea is this, that, the first instruction is going to take from this time, starting your clock down here and ending down here, right? So it's going to take whatever number of clock cycles that is. But once you've used the instruction fetch registers and you moved on to the decode register, right? That instruction fetch register can be reused for the next instruction. So you bring it in, why waste time, okay? And so on for all of them, right? Okay. So if you're a design engineer, a systems architectural engineer, right? Those waveforms are not going to help you, but this one will, right? So you start designing your ALUs, your registers, and everything else, keeping in mind that you want to get as much parallelism out of the system as possible. Now, the very earliest CPUs with the pipelining in them were 8-bit 6502 series, in the 1980s, right? So this is actually quite an old technology, right? People are looking at parallelism way back there several decades ago. All right. By the time of the original Pentium, 1991 or whatever it was, Intel's Pentium, right? They had taken this technology within 10 years from the 6502, right, to a stage where they had 35 stage pipelines operating on the first Pentium. Okay, that's a nightmare to handle. Absolutely not, but they did it, right? And the Pentium was a very high performing class of CPUs back in the early 1990s. Okay. What does this buy you, right? Because a lot of engineering effort, design effort goes into making sure that these pipelines operate properly, right? Just having a pipeline doesn't guarantee that there'll be a speed up, which is perfect. A perfect speed up would look something like this: that you increase the number of stages, and your speed up goes linear like this, perfectly linear, right? Okay. It doesn't work that way. Of course, you could be very lucky and could be super linear. You get a greater than 1 performance increase, but that doesn't happen. Now, in reality, what happens is this: your speed up factor has to be compensated by the number of instructions that you can handle on any pipeline stage. Okay, so if your number of instructions starts to increase, and you have an increasing number of pipelines, then instead of getting this perfectly linear curve, you get these curves which are not linear, and they start to saturate. You can see that they're starting to bend towards the horizontal already, right? So again, the law of diminishing returns. After all that effort, right, you have to put a stop to this thing, because you're not going to get the performance that you want. All right. Okay, and if you were to reverse that, if you looked on the number of stages here versus the number of instructions, again, the same sort of kind of thing happens. Saturation starts to kick in after a certain value. Okay, so that's the design engineer looking at things from the pipelining point of view. What other opportunities are there if you're a designer, if you're a CPU designer? What other opportunities do you have to extract as much parallelism as you can? Remember, the software engineer is not going to do this for you, right? He's just writing a code, a bunch of sequential code, because that's the way he thinks, right? But you as a hardware engineer, right, you have to think parallel and try and extract as much parallelism out of that sequential code as you can. So we've already looked at the fetch execute cycle that has a natural way of bringing parallelism in, but there are other opportunities. There's data level parallelism as well, where you look at the data that's being thrown at the problem, right, and see if you can if there's something in there which allows 2 bits of data to be acted on at the same time. So that would give you data level parallelism. You can also have task level parallelism, where different tasks are allowed to be run on multi-core CPUs at the same time. Job level is basically an extension of that, but for distributed systems. And there's memory level as well, because memory is one of those things which involves communications, and therefore it's a bottleneck to computation. All right. And if you can speed up the memory or parallelize the memory transactions at the same time for multiple instructions, you get an obvious way to parallelize stuff over there as well. Okay, what about process improvement? So we looked at architecture. Architecture can be designed in such a way to get as much parallelism as you can. But what about the actual manufacturing, right? That's what I mean by process improvements. The manufacture of CPUs is an incredibly complex task, and I have a 6-minute video at the end to show you exactly how complex it is, right? But let's just for now play the gigahertz game. Anybody remember when the transition from megahertz to gigahertz happened? Which decade was that? You know, in the early 1990s, you could buy a 75 megahertz compact machine, I remember, right? Which was state of the art, 75 megahertz, okay? And within 2 or 3 years of that, you find that, you know, instead of going for 100 megahertz, they just went into 1 gigahertz all of a sudden. What happened there? What happened was this, that, you know, behind the scenes, these manufacturing giants, Intel and AMD, they were working on improving the process, the actual manufacturing, which allows you to, you know, shove more and more gigahertz out of the system, right? Oops. Yeah, okay. All right. So for a single processor system, we're looking at this era here of 1986 to 2002, you were getting about a 50% performance increase every year, simply because they were upping the clock rate from, you know, 25 gigahertz to 30 to 40, 50, et cetera, okay? But eventually when they started doing the gigahertz game, then you found that, you know, the performance increase was not that substantial. From 50%, it went to about 20%. What exactly happened? Can you think of a CPU today which does more than 5 gigahertz? Is there such a device on the market? There isn't, is there? Right? The best game systems you can buy, NVIDIA, whatnot, they stop at about 4.7, 4.8 gigahertz. If you overclock them, you get 5.1, 5.2, right? And the same thing happens with CPUs. The best CPUs you can get are about close to 3 gigahertz. Why hasn't anybody come up with a 10 gigahertz CPU? Can we not build these things? And the answer is no, we can't if you're using silicon, because silicon has physical limits. The physics of silicon comes into play and restricts you from pushing the clock rate to such an extent that it becomes unaffordable in terms of the heating. Again, the law of diminishing returns. You get to a point where, you know, putting more effort into the design is not going to give you any benefits. Okay, so the physics also tells you that the clock rate in hertz is proportional to the power in watts. So the more gigahertz you try and extract out of the system, the hotter it's going to get. As it is, on a standard 2.5 to 3 gigahertz CPU, the heat sink is so large, right, that it takes a significant amount of power to just keep the system cool. If you didn't have that heat sink, right, it would be hard enough to fry an egg, literally. And there are videos you can find on YouTube which actually show you that, you know, you can fry an egg on a CPU because it's hot enough. Okay, and the energy efficiency is inversely proportional to the clock rate, okay? So it makes no sense, law of diminishing returns, to up the clock rate beyond what we have already, okay? So for the past decade or so, we have been stuck at close to, you know, 5 gigahertz, and we're not going to move from there unless, you know, something drastically changes. What's likely to change? Any ideas? He said in 2025, Moore's law comes to an end, we expect, right? So we could potentially transition to some element other than silicon, you know, germanium arsenide being the most obvious choice because it has very solid properties, very similar to silicon, but, you know, it is capable of generating, withstanding much greater heat. All right, so that's one way of looking of anticipating that, you know, things will improve if we decide to go from silicon to another material. But the problem there is that, you know, we have decades and billions and billions and billions of dollars invested into the silicon infrastructure. To change that to gallium arsenide is not going to be cheap. It's not going to be fast. It's going to take time, right? So we'll see what happens in 3 years, you know. But the expectation is that you know, things will continue around the 5 gigahertz, probably until the end of the decade. Okay, so process improvements. This doesn't mean, by the way, that, you know, people are still not looking at extracting more performance out of silicon, but all the effort that is now happening is going at the gate level, right? So a transistor consists of three parts, which you know, collector, gate, and emitter, right? Okay, so the gate is basically the gap between the collector and the emitter, right? And if you can narrow that, right, the distance the electrons have to flow from the collector to the emitter narrows, and that gives you greater speed. Okay, so that's where all the effort is going now. So when you hear about 5 nanometer, it certainly does. Quantum effects kick in. Yes, I agree with you. Okay, right, but that's an entirely different subject, right? Okay, and who knows? Quantum computing actually exploits that rather than treating it as something to be handled carefully. It actually makes use of that to solve problems. So maybe we'll end up actually using those quantum effects to Okay, just to show you that this gigahertz game, right? That I said we are stuck at 5 gigahertz, and the law of diminishing returns. Keep that in mind, right? It doesn't really make much difference if you solve a game problem running at 2 gigahertz to 5 gigahertz. So let's just run this video. So this guy he's done a comparison for clock race from 2 to 5 and see what happens. See, oops. Yeah, I want to run that video. There we go. Yeah. You really can't tell the difference. Okay, so unless you're really sharp-eyed, you might notice a few frames here and there, but this for the average user, right? 2 gigahertz is as good as 5 gigahertz for gaming, which is one of the most computing intensive applications you can think of, right? Okay, right. So now we come to computation versus communication. So AT&T Bell Labs 1948. This was a very special place and a very special year because two significant things happened at the same time. One was the invention of the transistor, right? It was first invented at Bell Labs. These three guys went on to win the Nobel Prize for the invention. And the press release that AT&T released at that time said that we expect that this invention is going to lead to some significant changes, and they were right. Okay. At the same time, there was this guy called Shannon. He was a mathematician and an engineer, and he was also working in the same labs. In 1940, at the same time, he published this paper, which is one of the classic engineering papers of all time, called the Mathematical Theory of Communication. What he did was, he basically said that, look, all communications involves information, and information can be represented as bits, ones, and zeros, okay? And therefore, suddenly, he started to unite communication, which was until then a purely analog thing, and computation, which is basically ones and zeros, okay? So this is the beginning of a merger of communication and computation. But they have been in conflict even after this merger, right? So there's this thing called convergence, which has been a big thing for the last couple of decades, where basically everything is now done in terms of bits and bytes. So today, if you were to go and design a new communication system, you wouldn't dream of having it analog. It has to be done in bits and bytes. Why? Because they're easier to handle. They're easier to error correct. They're also easier to transmit, right? Give you an example. The Voyager aircraft, right, which was launched in mid-1970s, I think. It's left our solar system. It's still transmitting. We are still getting the signals back. And recently they had to make a correction, and they sent a signal. They weren't sure it would work. It actually worked. They sent a signal back, and it made the correction, and they got the feedback as well, right? So imagine that this device is now outside our solar system, and sending all these bits. So the signal that arrives at Earth is an extremely faint signal. It's a digital signal. And the only reason they can actually make any sense of the signal is because they have these mathematical error corrections going on. If it wasn't a digital signal, if it was analog, we would have lost contact a long time ago, right? So that's how powerful this theory has been for us, right? Just the ability to communicate using bits has been one of mankind's greatest achievements. Okay. Communication slow down computations. Okay, so I think that's a bit obvious now, right? So just to drive this point home, the 5 most common throughput bottlenecks are as follows. Now, what is throughput? Throughput is the ability of a system, right, to do a set number of tasks in a set amount of time. Okay, so you want system with high throughput all the time. Okay, you want a system to be able to solve a large number of problems in a given time. Remember, we're trying to compress time all the time, right? Okay, so the 5 most common bottlenecks are CPU utilization, which basically means that if your CPU is busy somewhere and you give it a new task in multitasking systems, it won't be able to handle it, and you'll actually experience the slowness of the system. Then you have memory. Memory is basically input-output. It's communications, right? If your memory is slow or otherwise busy with something, right? This is the second thing which is going to slow down your system. Your throughput will be reduced because of this. Then there's the network bottleneck. Of course, network is even greater communication than local memory, right? So you're communicating across the room or whatever, especially if it's wireless, it's even worse. If your network cable or your network system is unable to handle the amount of data being thrown at it, your throughput will experience a slowdown. Then there are software limitations. Software limitation is basically a special case of the CPU utilization. If your software is not written properly to handle these situations, again, the throughput goes down. And finally, disk usage. Disk usage is the worst of the lot because disks are the slowest part of any computing system, right? It's a mechanical system, right? Even with the solid state disks, because it's an external device, it has to go through a series of interfaces before the data can be fetched or you can do something with it. So because of these intermediate stages, right, communications does have a significant impact here. And in this case, convergence between communication and computation does not help, right? Even though everything is binary, everything is being in terms of ones and zeros, it doesn't really matter simply because of the overall architecture getting in the way. Okay, software. So I'll just have a slide on this, old school versus new school. So what about software, right? So we've talked about, because I'm looking at things from my perspective as a hardware guy. I tend to avoid the software side, leave it to the programmers. Okay, so there's an old way of doing things and there's a new way of doing things. Okay, so what about software? First of all, you have to realize that for high performance computing, Linux is king. Every system which is high performance these days works on some flavor of Linux. Yes, it is heavily customized, but it is Linux. Linux is quite capable of handling multiprocessor distributed systems at a kernel level. Okay, so that's great because there's a lot of expertise in Linux out there. What about shared memory versus distributed? First of all, let's distinguish between the two. Distributed memory is basically where you have a CPU and the memory is distributed across multiple systems which are physically separate. Okay, and shared memory is where you have multiple CPUs, but they are sharing one block of memory at the same time. Okay, so if you're dealing with a shared memory system, you use these libraries called OpenMP, right? And if you're dealing with distributed memory, using MPI. So both of these libraries are open source, Linux based, freely available, and versions exist for just about every CPU out there, right? So in other words, if you build a fantastic machine and you're worried about software, well, don't worry, because all these libraries exist. It's just a matter of customizing them for your particular design. Okay, so this was the case until about a decade ago when the GPU revolution really kicked in. Graphical processing units. These things began as gaming engines to help out gamers. Okay, and the idea was that games involve a lot of multiply and accumulate operations, which, by the way, is 99% of all high performance computing applications as well. They're all multiply and accumulate. Interestingly, right? So the GPU revolution basically meant that NVIDIA came up with this library called CUDA, which is an extension of C. It's the most popular programming language for GPUs now. So now when you have a GPU in your system, it's not there just to help you in your gaming. It's there to actually solve difficult problems as well, right? And then because of the success of CUDA, the people who are behind this came up with something called OpenACC, which basically allows programmers to program GPUs with syntax similar to OpenMP. So, if you're familiar with the syntax and you want to transition to a GPU-based device, don't use OpenMP or use this another open source library. So they made life easy for you, right? Okay, so life is easy in the sense that, if you're a software engineer, you don't have to start from ground zero. You have these libraries, customize them, use them. Okay, so how much time do we have? Okay, no, I don't have all the day. Compressing time here. Okay, all right. So this is the final stage. So this is I said before that, look, this was supposed to be an open discussion. I'm really interested in this, as Dr. Saab mentioned, that 15 years ago, we tried to get a high performance computing culture going in Pakistan. Nothing happened, unfortunately. But maybe this is a second opportunity here, right? So I'm going to start off by showing you this little video of how computers have evolved from the 1930s to the present, 2020. And what is being shown here is basically the IPS, instructions per second, up to the year 1961. And after that, the flops kicked in, the floating point operation per second, because this is the way to measure your high performance computing performance. One thing you should note here is which countries are dominating this. So the Chinese started making an appearance about a decade ago. That's significant because they held that top spot for 5 years until very recently. And they came out of nowhere, really. So if they can do it, surely we can. Okay, so June 2020. Now, this is the website which is the go-to site for all high-performance computing enthusiasts, right? This basically has a listing, an up-to-date listing of the most best-performing computers in existence on any given date. So, I'll leave it to you to figure that out. So what I did was I actually took a screenshot. I don't think it's visible, unfortunately, but this is as of today, this morning, right? The top-performing computer at the moment happens to be a Japanese high-performance supercomputer, right? Followed by the Americans, and I think the Chinese are at the. I can barely read it myself. I think it's the fifth one at the moment. Okay. How do we do this? If we had, let's say, I anticipate maybe, I don't know, a couple of $1 million to build a high-performance machine. Can we do it? How would we do it? Well, we would do it using something called a cluster, right? Because what's happened is that in around 1993, 1994, the law of diminishing returns kicked in again. It became somewhat unworkable for these big companies like Cray and supercomputing companies like HP and whatnot to start developing their own CPUs, because Intel and AMD were doing a much better job of it, right? So what they did was they closed down their entire CPU department, and they started buying these off-the-shelf CPUs and concentrated on building clusters of systems, right? Let's get thousands or hundreds of thousands of these CPUs, put them together. Let's get them to work together and lower the communications overhead to get a supercomputer. And that's the way supercomputers are built today, which means that you and I can, given enough money, we can buy these off-the-shelf parts and we can build our own. It's not impossible because you're not designing a CPU from the ground up. Okay. And the first people to do it was this group, which involved these guys called Ratajkowski and Ed Line. They came up with a system called Beowulf. It's known as the Beowulf cluster. But this is the prototype which basically kicked in the modern supercomputer high performance computing revolution, because they basically were looking at solving a Linux problem, not a high performance computing problem, right? They wanted to see that if you build a cluster of these off-the-shelf CPUs and put Linux on it, will it perform as an operating system? And the answer was yes, it does perform extremely well, because Linux, one of the great things about Linux is it has this IPC, inter-process communications, built in on the kernel level, right? So that allows you to optimize and minimize your communication. Remember, the communications is the killer, not the computation speed. The communication, if you can lower that, your performance goes up. Okay. Now, this is a short video, about 3 minutes, I think. of an IBM supercomputer. Is there audio on this thing? Will it play the audio? Yeah, it will. Okay. All right. Now I want to show you that this was designed by IBM. This is a cluster, Beowulf inspired cluster, designed by IBM, right? And what they do is basically they take racks of these things, of CPUs, right? They combine them with storage racks and networking racks and put everything in a big case, right? And then they duplicate the cases. That's pretty much all you need to build a high performance computer these days, as long as those storage devices are communicating with the minimum bandwidth. So I'll let her do the talking, but it will give you an idea of two things. One is that these things are still fairly complex from a hardware point of view. The second thing is that in spite of that, it's doable because everything is off the shelf.
So this is a Z14 double wide. So I probably will say at a glance, we're going to show this is power we have behind this. More power, I see up there, IO and our processors. Stand away. Up here, this is my power supply. There's two batteries up there. We just know what the batteries are, they're kind of small. They do a very specific job. The power goes out. We want to make sure that we complete transactions to the site, right? The data density is incredibly important to us. Any complete. Right? Over here, you see this nest of IO. These are all PCIe IO cards. You can see that we have a ton. We have even more on the back. There's some over there too. And if you just move the rest, it goes down the seven to the bottom. These are where we have also IO. We even have DMC for data compression. A lot of pressure, a lot of jobs, moving a lot of data. See more IO cards, like I said, more on the back. Now, if you look, we talk about open IO, right? We have a switch pretty on that where we have done this activity going on that we need this. It's incredibly complex. And why do we do this? Take a peek at this thing, okay? This is the light card, right? So this is the working on the train, right? And you know, the IO card is like that, or maybe you just want to upgrade one. Maybe you'll probably try a CT, but you're working remote. What you're gonna do? You can actually talk to the FC and light this up. This will actually point to on-site technicians. Just to the location now, real quick. Over here, over here. There's a light bulb for people as well, right? So that allows you to just, very easily communicate where your technician needs to go. Now, I mentioned the FT. The FT does a lot more than making light. So, an airplane, right? You ever seen a cockpit? Full of knobs, right? Like, everywhere. That's what the FT is at a glance. So you think about this huge frame, these are so complex, right? You saw those wires, you see this massive. The FT does. It's the buttons and knobs of the airplane, right? You should think about an L-car. Well, what you can do for an L-car, number of processors, how they share, they're dedicated, how much storage. And certainly, there's people having real estate for that necessary. And if it's huge, I can live in it. So you don't want to handle that, right? You want to deal with all the time. Allows that level of control and both and we spoke about the agency, so the command line system. So right here, we have two of them, right? Just like two pilots on an airplane, but then it's the two FT servers are out here. So if you have one and you lost it, you're gonna land that plane gladly. So that's FT. Very good. Right, so now we have 4 drawers, right? 1, 2, 4. Each drawer itself has 2 coolers, pushing in cool water, taking out contact. Here, you get a continuing radiator that's cooling, warm air is flowing in the back, which I think I'll show you. So let's do some quick math, right? Each one of these drawers has 5 chips. Don't be confused. Each chip has 7% cores. So let's take the lowball processors available, right? 5 times 7 times 4, that's 140 processors. 140. That's a lot. So I want to show you the back so you can see how this thing's been cooled. So this is an absolute wind tunnel. This is a nice summer breeze. This is behind the processors. They're all getting cooled and this air is coming out hot. So she is working very hard. And as I promised, more cards on the back. She's nice and warm, actually. And those are the back of our power supply. And look at the nest too. Remember the other side, we have just as many over here. So where are those wires going? We have network, right? But we also have storage. This is the back of one of our storage units. You can see just as many wires, right? Not as interesting from the back. You can see the complexity of the network that's hooked into this. This machine is not just hooked online, but hooked to many of the things we have on site. Right? And this is the front of our hybrid storage. Now, it looks pretty, right? Look here. Every one of these storage trays is full of what? Each one of these slots has about 2 terabytes of storage. I'm not even going to try to do quick math and add that up. We have so many of these. What are these guys over here? If you look closely, you can see these are all, this is flash, solid state. So we have tons of storage going on this. These guys are incredibly fast, working on fast networks with those fast PCIe cards. And since this is hooked up to so many things on site, remember the SC? We had a computer for a computer. We did it again. Right here, this guy controls the storage, like the data. So every machine that hooks up to this doesn't want to worry about what everybody else is doing. This guy handles your data integrity for you at a very, very, very good performance, which is really incredibly important. We're dealing with spinning storage. So yeah, so backing up, I don't know if you want to take a glance at like the machines we have here. We've got a lot, okay? Just like that Z14, we've got like 20 in the back. And that's just one floor of one building here at the Poughkeepsie Labs. So a lot of work being done at any moment, a lot of machines turned on, a lot of warm air being blown up back. So thank you. I hope this inspires you to learn a lot more about the mainframe. So you can see they're incredibly complex and have fun with it. Okay, thank you.
Okay, some key things to note about this video. One is obviously that, like I said, they're using these racks of CPUs, right? Okay, you can buy them off the shelf, except that these days you wouldn't necessarily go with CPU, you just go with GPUs. NVIDIA has an entire ecosystem of this available off the shelf. They sell to anybody. So, we can just pick up a whole bunch of them, right? And start the process. Next thing you need is obviously storage. They talked about SSDs, right? That's the fastest available external storage that we have. She didn't actually mention RAM, right? But what happens in these big clusters is that the RAM is actually part of the GPU board itself, okay? And there's no such thing as a shared memory in these, it's mostly distributed memory, okay? So again, it boils down to the question, how fast can you communicate between one of these boards and others? It's your communication bottleneck again. And the communication system that you want to use is something called InfiniBand. It's another open source, it's not open source, it's commercially available, right? And there are many suppliers for it. So, you can get these InfiniBand chips and you start wiring things up. Finally, there's the heating thing. She talked about the heat, right? Because these things generate tremendous amount of heat, right? Okay, so you need a water cooling system, which is linked into the building. And what a lot of these companies do is they take the heat generated and recycle it to heat the building, okay? So they put something in and they get something out as well. Okay, now we come to manufacturing. This is about a 6-minute clip from a news item, which basically shows you how difficult it is to manufacture actual chips these days. The manufacture of chips is an extremely complicated thing. It's much more difficult than trying to set up a cluster. Okay, the fabrication plants that we have today cost tens of billions of dollars for each plant, and they have a lifetime of maximum of 5 years because the technology is moving so fast. Within 3 years, you have to start designing the next set of fabrication plants, and 2 years after that, you basically throw that away and they're at the cutting edge of more stuff for sure. Yeah. Okay. Tremendous amount of efforts over decades has gone into setting up the global chip manufacturing infrastructure. And now what we have is we have a lot of consolidation in this industry. Certain companies now basically hold the world by the neck, as for the Taiwanese especially, right? TSMC is you may have heard of them. Yeah, they are one of the they're in fact the leading manufacturer of chips today. And there's a Dutch company which manufactures one of the plasma etching devices, which the likes of TSMC use for their manufacture. So watch this video. It's highly informative, and hopefully at the end we'll see that this is something that we can easily do, right? Unless you have hundreds of billions of dollars lying around.
Enough to take you inside a clean room that's building an engineering marvel that'll push the entire electronics industry to the next frontier.
They're both amazing and scary. They're really enormous. It's something that you don't necessarily see.
It's not the size of say over 180,000 kilograms, but over 1,000 volts and 2,000 watt cables. Pop the lid, and you'll see this machine generating plasma that will get collected and reflected by a series of mirrors to then continue to scale patterns onto chips that will eventually go into your cell phone. And after 30 years of applications of physics, chemistry, and material science, it's about ready for its time. An integrated circuit or chip is one of the biggest innovations of the 20th century. It launched the technological revolution, created Silicon Valley, and everyone's got one in their pocket. But if you zoomed in on one of those chips, you'd find a highly complex nanoscale size city that's expertly designed to send information back and forth.
Something that we're going to out and saying together. You start with certain and insulators, you add something called gate, which you apply voltage to flow of electrons. That's what it's for the best zero ones you always hear about.
Do that sequence of light. The network streets and buildings make these transistors manipulate those transistors. You turn that into something that has some state or that
At big tech conferences, chip manufacturers will announce they can impossibly small milestones, like 22 nanometer, then 14 nanometer, and 10 nanometer designs. That means they found a way to shrink the size and increase the number of features on the chip, which ultimately increases the overall processing power. This is a drum beat called Moore's Law.
Moore's law is an expectation, not an actual. It's an expectation of an at a pace of roughly doubling the speed. All of those things allow us to allow cheaper price. That is the price of the that means
we're able to create more all the circuits before having smaller.
Moore's law has been dying for a long time, and it never is because knows their expectation to keep going.
Expectation is called photolithography. It's a chip manufacturing process that's similar to technology, but instead of a negative pressure, they're using something called a mass flow measurement to expose the geometric lines.
That's a creation system with light source, a mass, the vertical, the main to one. Perfect extraction and so then I teach the builder of human with a night function.
The light sources are lasers created with a mixture of gases like carbon dioxide or argon fluoride. When excited by an electric current, the gas molecules will emit laser radiation that are then tuned to the system that imprints the chip inside. It's tried to get the light source to shorter and shorter wavelengths, because the shorter it gets, the more transistors.
In terms of electromagnetic, what we can see visibly from 400
The chip can see from 365 nanometer wavelengths to 248 to something called
so the virtual light produce visible ultraviolet laser.
It was tried by 107 nanometer line, and that failed after hundreds of millions of dollars.
the field then has to invent new techniques in use today.
We actually put water between the bottom and the top. It's the way that the light in water is quite short. I don't do that. You get water all over the stage as an electron tool. There was some very clever engineering that allowed them to have water. It's a way for it to pull back a little bit. Sometimes maybe it's a second.
That turns out
So to keep Moore's law on track without breaking the laws of physics, chip manufacturers have been racing to bring this technology online. Soon ultraviolet product. It takes the weight of the down to 13.5.
It's much larger than what we normally do, and that's partly because more disruptive. First, I did when I was still in graduate college, my whole career, we were hearing that movies. There was some fundamental problems. It's science, very we're down to the point where we have measured out, and so I worked very hard to have control of those.
And that is where ASML comes in.
ASML, that's the whole thing. We build big machines that have explosives. Even massive state where it's not only in a vacuum and at wavelengths where you need to have only the thing by a huge amount of energy. But we also need light source. In fact, the first time ever that we needed light source and huge elements.
But for this morning, we're just going to focus on the basics. Here's how they work in the machine.
Stores of the light, come with proper,
Small and defined by across the desert and being intersect roads with cultivate and critical accuracy just a few months, even on travel.
it forms a plasma that emits UV light. There's a collective mirror that collects that light and sends it through the scanner. And there are four of us that take that light into the slit that bounces off the rest.
This is a big thing with this, and what's happening is step by step. We produce that particular pattern over and over again. It's going to be a sense of mechanical the way the state of cells. Right, and look at inside of the cell.
This get the power.
We just started in channel and we struggle.
Every year it's slipping out and the actual power we get stuff around very low levels of crack.
To dive more underneath what we was around that finding all of that exactly control how you do the relations with droplet, then how you do it, pushing that. You don't just need to what one last point, two, first of the way shape the kind of enables us to get the right conversion. And then the second part of it generate that very generate so once we press the brake, every time I would say inspiration to solve it. You can see the new we actually still be there. Now, for the features or features.
What is it to require them? Because the Chinese chemical could kill a new pattern.
The major source of equipment, generally, unless something is actually sprayed and something is just fatal. Tools, wafers, containers.
You and lots of manufacturing tools associated with we also have so we have when we are looking at these resources, a lot of history, lots of connecting with gas, power, water, to see in transport systems where we have to bring the high power into the vessel.
ASML is shipping factories, and it takes 40 freight containers spread over 20 trucks and 3 cargo planes just to send one.
This was part of pushing for all, and then of course, the EV scanner is the most technical tool. It's so far from normal experience. I can't think of anything that is pushed on something here. Don't think all people feel
Where it's starting to get in the high end effect. And so, in fact, we're just starting to do products from that.
There's insatiable amount of data. You can build chip use more data, data, move data around the whole cloud. I just want this. Creates billions of things. There's no way to make sense of all of that. Even with this chipper, you've got to go build chipper back to larger data storage. Part of the future is around diagnosing trends. If you don't know the future, are you afraid of that, or are you encouraged? And I'm in the category of encouragement. These are things to do. And then you may have to help change the world. You change the world.
Okay, I think the audio was a bit off, and hopefully this video can go online. People can watch it later. Yeah. All right. Okay, but a few things to note about this. One is that you saw how they're using light to fabricate these chips, and the kind of tricks that they have to play with the physics of light to get as narrow a beam as possible. So they have these water droplets, and they fire lasers at the droplet as it's falling in order to convert it into a plasma, which allows them to focus the light on a specific length. Quite remarkable. It's that ASML machine is actually known as the most complex machine in the universe. There you are. Okay. One. Okay, yeah. So what can we do in Pakistan? We're not going to build one of these machines immediately, but maybe we can get started. I saw this article from 6 days ago, and it kind of drives the point home. Why do we need to go through these periodic media media reviews reports when we can, when we have enough talent in this country to be able to do this on ourselves by ourselves. Cluster machine is not an impossible thing with the kind of talent we have here, right? What's happening in our neighborhood? Iran, under sanctions for like what, 4 decades? They're into this game. Okay. And our best friends, the Indians, of course, they're in it as well. Okay, we'll look at something called RISC-V. This is an open source CPU design. I started off as a research project at the University of California, and it was such a successful project that they open sourced it. And the instruction set, unlike Intel and AMD and ARM, the instruction set is completely open source. So given this instruction set, you could actually implement a RISC-V processor on an FPGA device at home if you wanted to. Okay, or you could do an IP core and have it fabricated by the Taiwanese or somebody like that. Okay, this is the website for RISC-V. I urge you to take the time to get to know it. RISC-V is so successful that the classic textbook, Computer Organization Design, is now available in a RISC-V edition as well, right? And if you haven't heard of this book, well, you should have heard of it if you're into high performance computing. This is a company which is trying to do to RISC-V what the Ubuntu people did to Linux. So Linux is open source, but Ubuntu is a company we came along and decided to streamline the whole process and provide support and whatnot to anybody who wants to use Ubuntu Linux for business or for any other reason. This company is trying to do pretty much the same thing with the RISC-V architecture. The great thing is the CEO is a Pakistani guy. Okay, they're based out of the US. So maybe we have something to start working with. Okay, any questions? Yep.
Assalamu alaikum. Sir, I am Hassan Ali, instructor from CS department. Sir, I have a small question that how can we relate high performance computing with quantum?
Okay. How can we relate high performance computing to quantum computing? You can think of quantum computing as an extreme case of high performance, which is completely unconventional, right? High performance, as we normally understand it, is basically taking standard CPUs and GPUs, getting them to perform together, right? But quantum computing is an entirely different paradigm shift, right? It's basically like I was just saying to, right? Okay, you have these quantum effects when you start fabricating and working at micron levels, right? Quantum effects naturally kick in. There's nothing you can do about them. So far, we've treated them as noise, as something to be handled and managed. But not with quantum computing, because those quantum noise signals can actually be used to solving real problems.
Is realistic in near future or not?
Excuse me?
Is it realistic? Can we make
Quantum computers, well, there's tremendous efforts going on, and not all classes of problems are amenable to being solved by quantum computing, but for encryption and for long-range digital communications, secure communications, they're ideal. So the Chinese have done tremendous work on it. They've shown actual, electron states changing state in a satellite which are linked to another electron on Earth. Bell's theorem, as it's known in physics. They've actually shown that operating. The Google claims that they have something called quantum supremacy, which is basically quantum supremacy is a buzzword. It's basically saying that a quantum computer can be as good as a conventional computer for the class of problems that it's solving. They made this claim about a year, 2 years ago, but then IBM came along and said, no, your claim is not valid because of this and this reason. So we'll see how things go. Quantum operating systems are available open source from IBM, from Microsoft, from a whole bunch of other companies. There's a Canadian company which actually said about 5 years ago that they were going to demonstrate a real live working quantum computer. No, everybody laughed at them, but they actually did it. And they actually showed it solving a problem. So a lot of work is going into it. Anybody who's a young aspiring physicist, I would strongly advise them to get into quantum computing if they can.
Thank you very much. I have one more question. Similar question to that. DNA coding. Is it possible? DNA computing.
Biological system. Oh, that's something.
Thank you very much.
Sir, this is Mohammed Zaman from IT department, manager IT. Sir, as you talk about the computation with communication to achieve the HPC systems, do you recommend or suggest some model or framework because both are interdependent to achieve the HPC? So do you recommend some framework or model to ensure that their interdependency and to ensure their efficiency and effectiveness?
Okay, so if I understand correctly, is there a framework for managing the communications versus computation problem? There's no one framework. There are many frameworks. Okay, everybody tries and solves the problem specific to the kind of computer, high performance computer that they're designing. Because remember, even though we've all come to the agreement that a Beowulf-like cluster is the way to go, and it has been demonstrated because the top 500 for the last decade have all been clusters of GPUs, right? So it obviously does work, but they all came up with their own specific custom solution to the communication issue. And yes, if we had a lot of money and resources to throw at this problem, that yes, we would design something with our own communication framework. We would not necessarily go with InfiniBand, which is the preferred favorite for everybody, simply because it's high performance, it's relatively cheap, it's available. There are no restrictions on it. Yeah, but if you really wanted to go all the way, then I would just drop everything and go with optical communication, because that surely has to be the future.
Sir,
This is what I was going to say in response to the question of quantum computing. In the next years,
Optical, yeah. Yeah, yeah.
20 years ago, I would not believe it.
Yeah, yeah.
But now they have demonstrated they can play with optical gates.
Exactly.
With the
Yeah.
polarization of the light,
Yeah, yeah.
they can change. So if it is done, then we can use conventional computers using this optical technology, and then the algorithms developed for quantum computing can be applied on the course of computers. This has become a reality. I know quite a few groups in Cambridge and European and USA who are for the last 25 years, 30 years working on these optical computers. Optical computers.
Sir, I'm Salman Bashir from Computer Science Department. As you said that in high performance computing, our objective is to achieve parallelism. And in that the architecture does matter in that situation. When we say the architecture, we have different stakeholders, hardware engineers, software engineers, design engineers, and they have different perspectives, abstractions, and expertise. And my question is, how is it possible for them to communicate effectively? Or as a CS researcher, is it possible for me to assign the power of one experts to other by using some, by developing some interfaces or by developing some?
Okay, so nice question. It goes back to the very first slide. We talked about disciplinarity cross, then we said high performance computing is a classic example of cross disciplinarity, where multiple frameworks from multiple disciplines coming together. So I think if you really want to do it properly, then you should get everybody from the artists to the philosophers as part of your design team, because they will bring a perspective that we can't. Take, for instance, the new thing which is happening in medical research. They now have ethics committees sitting in on drugs design and stuff. They're doing it obviously for financial reasons because, they don't want to be sued if something goes wrong with developing medicine, right? But even if you throw away that money part, just the idea that, you're going to develop something which could potentially harm another human being, is wrong, right? Again, that's human nature, right? Okay. Another example is this, self-driving cars. Okay. You must have seen videos of self-driving cars, right? Cars which drive themselves. Okay. Here's an example. Here's a scenario rather. So a self-driving car is traveling along the road. Okay. There's nobody there. And it comes to a junction. All right. And out of the blue, a child jumps in onto the road from nowhere. The sensors pick this up, obviously, right? What is the algorithm going to do? It has a few choices. It can try and save the child. It can try and save the owner who owns the vehicle. It can try and save itself, the car. This is an ethics issue, right? So you build this amazing device. It's not really a car, it's a computer with wheels on it. Okay. But unless you bring this ethical perspectives and moral perspectives and philosophical perspectives, you will run into these problems. So I agree with you that we need to involve all these people, and how to communicate with them. Well, communicating in science is a discipline by itself. We need communications managers to probably facilitate the communications. Okay. So in a situation like this, self-driving car accidentally kills a child or, some passenger or whatever. Who pays? Does the insurance company pay the bill for somebody's injury because some software programmer got the algorithm wrong? Right. So all these questions, which are ethical questions, and they're highly charged questions. So we have no easy answers for them. And that's why this needs to continue as a cross-disciplinary subject involving as many stakeholders as possible.
I'm Faisal Aziz from IT department. Sir, during your talk, as you told that we are going to live with the same technology within this decade, and we can create the web of clusters, as you told, by setting up the required hardware and combining them up. So my question is that as many countries are now in the race, as you showed the video, that every year and now every other month, a new supercomputer is being set up, and you showed that now India and Iran are also in the race. So is there any technical barrier of this race where it will end, or what will be the future of this race?
I don't have a crystal ball. I don't know. We can only make intelligent guesses on where this will go. And probably the best example of that is Moore's Law itself. Because he was a physicist and he was involved with he had a good idea about the manufacturing cycles. He was able to make this prediction about the chip density doubling every 2 years. Remember, it's not a law; it was a prediction which just happens to come true. So can we make similar predictions about where things are going? Yeah, you can make intelligent predictions. It doesn't mean that they will be, they will turn out to be true in 5 or 10 years' time. We expect certain things to happen. It doesn't mean that they will happen. It's probably the best answer I can give you.
My name is Imran Baja from IT department. I'm working as a manager IT. As a software guy, my question is particularly related to the throughput bottleneck you have discussed in this session. I just want to know what kind of major issues you have explored during your experience related to that bottlenecks. And your suggestion regarding this to overcome these bottlenecks. That is throughput bottlenecks.
What are the bottlenecks?
What are the major causes we can identify? You have explored during your study, during your experience, and what are your recommendations to overcome this issue?
Well, the one thing which stands out every single time is the communication problem, right? Okay, unless we can crack that, and maybe optical computing is a way forward, we will always have this problem. I mean, if I was thinking as a designer, I really don't see a way around it, simply because locality of memory referencing does count, because why do we have cache memory L1, level 1, level 2, level 3 cache? Why do we have all this? Simply because we're trying to circumvent the communication problem by putting memory as close to the computational engine as possible. Distances do matter here. The electrons which flow through your CPU, they're not traveling at the speed of light. They have a physical limit. Okay. Yes, the signal travels, the electromagnetic signal goes at the speed of light, but not the electrons. Okay. So if you can shorten those distances, your communication problem actually does go down. Okay. So other than making the things even smaller and smaller, and then of course you get hit with the quantum issues, right? Somehow coming up with memory systems which are extremely faster than what we have today. There's really no way around it. No easy way, at least.
I'm Asma Abdul from Computer Science Department. I have a question related to AI. That high performance computing will end at the AI, or AI is going to give us the solution of the high performance computing?
I hope it doesn't come to that. See, the 3 talks over the 3 days are linked through the data science thing, right? Okay, so the next talk tomorrow, inshallah, is neural networks. Okay, which basically is the core technology behind the AI revolution as it stands today. Okay, as you'll see tomorrow, inshallah, the one thing which happened was in the early to mid 2000s, which made the AI industry what it is today, was deep learning. Okay, deep learning is basically taking a neural network, adding multiple layers in the middle, just like it is in the human brain. So all we did was we tried to imitate the human brain. Okay, now if you're imitating the human brain from a purely physiological and physical thing, right? Okay, but your question is more of a conscious thing, right? That will the AI become intelligent enough to be able to design our systems for us? I don't think it will. It can be a useful tool for it. There are already drugs out there which are being designed by AI simply because of their learning capabilities. What they do is they take an AI system and they show all these different drugs and the kinds of diseases that these drugs attack, right? And then they show it a completely new disease and say, okay, now predict what kind of drug is going to attack this, and it does come up with something. So this has already happened in the last couple of years. I don't know how successful these things are because drugs take about 10 years to come to market unless you're dealing with COVID, which is a special case, right? Will AI become smart enough to develop its own AI? If that happens, we better run for cover because it will not be a good world then.
मेरा सवाल शायद थोड़ा सा पॉलिटिकल भी हो ये और एंड दिस इज रियलिटी वो ये है जब मैं PhD करके वापस आया ना when I came back and then I had few meetings here and there I thought that high tech is going to be another area where we will get empowered. Yes, so my question is, what will be the safest number of flops our HPC can be made without getting an embargo? और उसके ऊपर जाएंगे तो वो जो आपने खबर बताई है ना, कोई हमें GPU भी नहीं बेचेगा तो कोई
exactly हाँ सही
memory storage memory नहीं बेचेगा.
सही.
That's a very critical question and I'm asking you this question because कुछ साल पहले हमें ना CERN के एक प्रोजेक्ट के लिए we needed to have Kentech 7 वो बोर्ड चाहिए था which could do 40 GB की communication कर सकता था at the rate 40 GB. पता चला कि 2 GB से ऊपर पाकिस्तान को कोई कार्ड नहीं बेचना. It took me 2 months to negotiate with them. If we are a university and we will place this card board in university और हमने CERN का project करना है.
Right.
So these days electronics is very easy कि आप IP हमें IP दें, इस IP के साथ ये लगा होगा board, so computer. So they can monitor कि ये board उसी physical location पे बैठा हुआ है कि नहीं बैठा हुआ, and what kind of job. So we got that one. So the same question is over here. If we start building our HPC, लोगों के कान खड़े हो जाएंगे. ये किस level का? Because the nuclear and the communication satellite या defense के अंदर है ना उसमें सवाल. तो ये बताएंगे कहाँ तक जाएं तो will be safe और उसके बाद फिर वही issues आ जाएंगे.
Right. Okay. So you're right. It is a politically charged issue, and yes, they will take those steps where this country is concerned. Or they always have. So we can expect the same behavior. next time as well. Nothing like being your own boss at the end of the day. We need to work on two things. One is get some culture of chip design in here in this country. Okay, I mentioned RISC-V for a reason. It's an open source instruction set. You don't have to pay royalties. You can take it, you can modify it, you can expand it, right? Design your own. Start with FPGAs, build up their expertise. Once you have that, start doing silicon course, which is intellectual IP course they're called. And okay, we can for now we can manufacture in this country, but Chinese are our friends. They have the ability to manufacture those for us. But also things like the Dutch machine, right, which is the most complex machine in the universe, as it's called, that's not even being sold to the Chinese. It's so sensitive. Okay, so what the Chinese are trying to do is trying to reverse engineer that, and they're very good at that. So we need a reverse engineering culture as well. Now, keep in mind that because the chip industry moves so fast, I said that every 5 years you have to throw away everything and start new. And to build a new factory is about $10 billion. Okay, and every 3 years you start planning for the next cycle. Now, when they start throwing all this away, some of that equipment could actually be bought through whatever channels. And I would suggest that we actually do this, right? So these Dutch machines which are used in the old fabrication plants, what are they going to do with them? They sell them off, and maybe we can buy them and start. I mean, there was a decommissioned particle accelerator operating in Jordan. Did you hear about this?
I know.
Yeah. Because somebody wanted to throw. Yeah.
We have a secret on.
Right. So if we can buy a decommissioned particle accelerator, then surely something like this should be possible. But unless you get that culture going now, we'll be in the same boat 10 years from now. So I think this should be done as a national priority.
So I just want to share now.
Yeah.
I just went out for a meeting, and that meeting was regarding preparing a national document or policy for electronics. Somehow they made me the co-chair of that committee.
Oh.
Which is, I don't know, it's a good news or a bad news, I don't know. But they want to have a national policy on electronics. I'm a microelectronics guy.
Okay.
I told them a story. In 1988, QDOS, Quick Design on Silicon, was a company in UK, and that went bankrupt. Uska ek jo director tha na was Pakistani, Dr. Haroon Ahmed. Probably you might have heard.
Oh, the Cambridge guy, Cambridge professor. Yeah.
Cambridge professor.
Yeah.
Mera bhi ustad tha. He said, I'm a director, company is getting bankrupt. मैं आपको ये पूरे manufacturing जो belt है ना, ये आपको 50,000 pounds में पाकिस्तान में लाके दे सकते हैं. अब 50,000 pound और उस वक्त महल 20 या 22 रुपए का pound था. 1988 की बात कर रहा हूँ. ना गवर्नमेंट ऑफ पाकिस्तान ने उसको हाथ पकड़ाया, ना किसी यूनिवर्सिटी ने हाथ पकड़ाया. Had this plant come to Pakistan, तो एक बेस बन जाने की माइक्रो इलेक्ट्रॉनिक्स.
Exactly.
And वो जो क्विक डिजाइन ऑन सिलिकॉन मैंने उस पे काम भी किया हुआ है. That became the foundation of FPGAs electron, because that used to give you 1,000 gates available on a single chip, so you can design your own integrated circuits of anything. But now FPGA has really revolutionized the electronics. So पहले तो आप software change कर सकते थे ना. Now you can change your hardware on the run as, and these FPGAs. ये I don't know. We still, मैं आप अभी वही कह के हूँ कि 50 साल लेट हैं हम इसमें. Malaysians made PCN in early 70s and they are happy now. हम अभी सोच रहे हैं कि हम करें या ना करें. And Chinese are there very clever. They are not going to give you technology so easily unless उनको कुछ चीज नजर आए, कोई advantage नजर आए. But this is not a bad idea to go with that. तो सिर्फ ये शेयर करना था. अब आगे देखने क्या होता है. But I think, I feel जैसे हमने थोड़ी nature has got its own timetable. अल्लाह ताला ने ना एक टाइम टेबल बनाया था, वो चीजें उस टाइम पे होती हैं. Probably this time is coming. Inshallah. We'll put the HPC together as well, and we'll do the electronics as well. ये बच्चों आप जिस जंक्चर पे इस वक्त आप बैठे ना, your role is very important, very important. अपने आप को डीमीन ना करें, लेकिन prepare yourself. ये सबसे जरूरी बात है. Prepare yourself. ये मैंने उस दिन भी बात की थी. इसी तरह का एक लेक्चर था, आप ही की एज का मैं होऊंगा उस वक्त. Then somebody, वो एक आया बता MIT से था, दोस्त, उसने
आके quantum devices के ऊपर था, and I decided this is the area I'm going to do my PhD. So I did microelectronics and this was PhD. So you might get an idea to do your PhD from there. Thank you very much, sir.
Quantum computing को भी कुछ करना होगा, because you know that has strategic implications for security and stuff.
उसके लिए मेरा the way the world is going on is
Yeah.
through optical computers.
Yes, but you also need good theoretical teams for that. But yeah, it's not just engineering. You need theoreticians, mathematicians.
I have one comment or suggestion. So we have seen the hardware side of quantum high performance computing. We wish we can have some insight into the software side of high performance.
I'm not a software guy. Yeah, yeah. So I mentioned the libraries which are available. They're all Linux based. They're open source. I've never had the pleasure of working with them. But
60% is continuing with the 70% that Sam asked. So
Yeah.
like building HPC locally.
Yeah.
So what do we have at home for this HPC?
I don't know what equipment have you got. I have no idea. But what I'm suggesting is this, that buy these off the shelf boards, right? Okay, and start building the systems around that. You don't have to go with 10,000 CPUs on the first iteration, right? Just go with 100 maybe, right? Get these and what is they called, the Tesla NVIDIA GPU, Tesla GPUs, right? For now, you can probably buy them until they put a ban on us, right? Get them to start the process. Right?
The person was really like instead of buying, so what do we need to develop?
You need chip design culture. You need software now, because this thing is done through software now.
This is the step for where we should start.
Ideally, you should attack both problems, because you should have the chip design expertise in this country, plus you should have the supercomputing expertise. Okay, now they are related, yes. Okay, but they are two different branches of the same subject. Okay, and unless you do both, you will come to a bottleneck in one of them and I wish I'd done the other one as well. And
That's the way we are self-sufficient.
Exactly.
Area, ways
Exactly.
we are always like,
Exactly.
they don't sell us.
But that's not a good excuse, I mean, if they didn't sell us, of course they won't sell us, right? I mean, the thing is, what have we done to prevent that?
First of all, thank you for giving me the chills by reminding me
Oh,
of the Patterson Hennessy book.
Yeah, okay.
And a lot of stuff that you covered while I was doing my MS. So my question, or rather a request, is that can you help us do a proof of concept of building a small cluster, so that what we really want to do is involve our faculty as well as students in building a small cluster which we can scale up and then use it for different research purposes and the university needs.
Yeah, I'm hoping that something will come out of this meeting. If the funding can be arranged, then yeah, sure. I mean, we can start placing orders and get a team who is capable, some electrical engineers and stuff. Because you need to, ideally the way to do it is basically don't just buy the SBC single board computer, just get the chips and then build your own board, because that will give you greater expertise in how to wire up GPUs. Okay, so we can do our own, and I definitely think we should go with this RISC-V initiative that Pakistani guy I mentioned was the CEO, because they're making an entire ecosystem available, just like Ubuntu, and we should get in touch with them.
We will discuss more, but
Yeah.
From a research point of view, from short projects point of view,
Yeah.
हम students को दे सकते हैं. The one which you are saying is like the one which can we come up with a commercial product or a product which can be used readily. एक जो है ना इस वक्त पाकिस्तान में इसे मतलब मेरा नहीं ख्याल कोई HPC के एक्सपर्ट्स पाकिस्तान में एग्जिस्ट करते हैं. क्लेम जरूर करते होंगे तो जिसने हैंड्स ऑन काम करके बनाया हो क्लस्टर और ग्रिड्स के ऊपर काम.
Unless somebody has done it as a hobby in the bedroom, yeah, I agree. Yeah.
I know people. सर में हमने काम किया है. सर में भी कंप्यूटिंग के अंदर अगर वो इन्वॉल्व हुए थे तो उन्होंने
we got involved. So we established a node in Islamabad and we operated over there. हमारे कुछ लोग जाके वहाँ पे ट्रेनिंग लेते हैं, लेकिन एक बंदा जो 10 साल जिसने पूरा सिस्टम इवॉल्व किया हो, उस तरह के लोग हमारे पास नहीं. No, what I had in my mind, जिसको मेरी आपसे बात हुई थी, मैंने ऐसा डिस्कस किया कि हम अपने बच्चों को कोई इस तरह की एक ट्रेनिंग दें यार, ये लेट्स नॉट गो फॉर जीपीओ, लेकिन मार्केट में आपको ये मिल जाते हैं प्रोसेसर्स बोर्ड मिल जाते हैं, हाउ टू पुट देम टुगेदर. यू हैव गॉट एसएसडी डिवाइसेस भी मिल जाती हैं आपको, रैम बोर्ड्स भी मिल जाते हैं, हार्ड ड्राइव भी. So you make your own cluster of 10 CPUs or
That is definitely doable. In fact, there are guys here who are doing crypto mining, cryptocurrency mining, right? हाँ, तो वो तो
हम ये टेक्नोलॉजी अपने बच्चों को किस तरीके से ट्रांसफर करें, बट वी at the same time the university should work for developing its own main HPC.
Yeah, but if you get enough people interested, you get enough people interested in crypto because that generates wealth. You can set up a Bitcoin or Monero mining rig, and as long as you're mining them properly, you're part of no one person can do it by himself, but you become part of the network. And there are guys in Canada I know who have built these GPU based devices, couple of machines, and they're making $100-200 easy a day just for nothing, just because they set it up, right? So $100-200 a day in this country is worth something, right?
Effectively, it's more than that.
Yeah. So the lure of money could actually be put to good use here.
Maybe that will be wonderful. I think it's small, and I'll answer that. For your swap. What share we can do it.
My name is Mohan from the business department. So like what's called custom machine, and facility law it's dependent on the this separator of the connection. But if we go to the cooling, we have any practices from abroad. We cannot import the hardware. So but if you do the cooling, people in Pakistan are already having passing capability. What if we find the mass mining, we mass cooling? What if we add the nodes like smartphones and
Yeah, no, it's a great idea. Pooling is used very heavily in the mining industry. The problem is when I last checked, maybe Professor can clarify this. I believe that Bitcoin has been banned in Pakistan officially. Is it true? It's not.
It has been evolved, and they are now mining.
Okay, there are people, but okay, fine. All right. So as long as it's not illegal, right? I mean, you can certainly create your own pool and and join the international groups, because right now it's not possible for one person to mine a Bitcoin by himself simply because of the competition is so great. But you can become part of the pool, which is global, right? And start from there. Because there's the reward of money, and that should get people sufficiently excited to actually work on it. But you also mentioned about smartphones and stuff, right? And that's something called grid computing, which was a hot topic about 15 years ago. It no longer is. But grid computing is basically exactly this: that you can put some software on your mobile devices, on your tablets, whatever, and when you're not using those devices, the code is running and doing something useful for the pool. Yeah. So depending on the class of problem that you want to solve, that can be quite useful. The classes of problems that where it is being used for is obviously for Bitcoin mining, for other crypto mining, for SETI, the search for extraterrestrial intelligence. You can go to the website and download software, and it will run this code behind the scenes when your machine is not doing anything, and contribute to the overall solution of the problem. So if there is a problem in Pakistan which needs that kind of computing power, yeah, we could probably write that and make it available to every citizen. It's a good idea.
Sir,
Alexander.
I'm Rambal from Computer Science Department, and pertaining to the computation versus communication trade-off, you just mentioned that communication slows down computation. And like we know that we have designed many systems for specific purposes, like real-time system, embedded system, time shift system. Why can't we design such systems which are specific for computation so that it will not be slowed down by the communication?
You can do that simply because of the nature of dependencies in parallel code, right? So, X happens after Y, and there's nothing short of an act of God which will change that, right? So you can't really get around that issue. People try and compensate for it through all sorts of clever tricks. Everything that we've talked about, instruction level parallelism, it's just a compensation way of, addressing that issue. But if something is dependent on something else, there is nothing you can do about it because that's a natural limit, it's a natural law, right? Thank you.
Thank you very much, sir, for the valuable sharing. Now I invite Dr. Mr. Ehsan Puri for the sharing.
Bismillah ar-Rahman ar-Rahim. We just had a workshop last week on data analytics. तो मैं बात रिपीट करूंगा जो मैंने वहाँ भी कही थी कि मुझे बार बार हमारे फाउंडिंग डायरेक्टर की बात याद आती रही कि वी आर सिटिंग ऑन अ गोल्ड माइन, विच मीन्स कि यूनिवर्सिटी के पास कोई 20 years का data accumulate हुआ है regarding students, how students study at the virtual university. Since this is a very unique university in Pakistan, it's completely based on ICTs and e-learning. So, माशाल्लाह डॉक्टर भट्टी ने अब हमें एक कह लें कि लाइट दिखाई है कि इन चीज़ों पे अब हम काम कर सकते हैं, डेटा एनालिटिक्स पे, HPCs पे, न्यूरल नेटवर्क्स पे, इवन डेटा विजुअलाइजेशन, ये सारे वो सब्जेक्ट्स हैं जिस पे कि हम बड़ा इफ़ेक्टिवली काम कर सकते हैं. प्रॉब्ली और यूनिवर्सिटीज़ के पास वो डेटा भी मौजूद नहीं है और वो कैपेसिटी या डाइवर्सिटी मौजूद नहीं है. और वर्चुअल यूनिवर्सिटी के पास ये बड़ी यूनिक अपॉर्चुनिटी है कि इन सारे सब्जेक्ट्स को आगे लेके चलें, उस पर रिसर्च करें, अपने स्टूडेंट्स को इन्वॉल्व करें. स्पेशली व्हेन वी टॉक ऑफ वर्चुअल यूनिवर्सिटी स्टूडेंट्स, तो उसमें बहुत सी डाइवर्सिटी मौजूद है और स्टूडेंट्स आर सिटिंग अक्रॉस द कंट्री और ना सिर्फ कंट्री में बल्कि अब्रॉड. सो वी आर वेरी यूनिकली पोजिशन to take advantage of all these areas. So I would really encourage our faculty कि इन एरियाज में रिसर्च शुरू करें और अपने स्टूडेंट्स को इन्वॉल्व करें, स्पेशली बिकॉज हमने एक्सपीरियंस किया है कि हमारे कई स्टूडेंट, जैसे आपने जिक्र किया, कई स्टूडेंट्स हमें नज़र आए हैं वेरी ब्राइट, वेरी दे आर, सिर्फ उनको थोड़ी सी इंकरेजमेंट चाहिए और थोड़ा सा प्लेटफॉर्म चाहिए जिस पे कि हम उनको लेके आएँ तो वो बहुत कुछ कर सकते हैं. जैसे आपने कहा कि RISC-V के CEO एक पाकिस्तानी हैं, तो वो हमारे में से ही निकल के गए हुए हैं. You yourself, बहुत से एग्जांपल हैं हमारे रेक्टर्स, और we can do it, we just need to believe in ourselves. So I would really encourage you. I thank you, Dr. Alawi, for giving us this opportunity of listening to a very, enlightening talk. Dr. Nasir, for arranging this workshop, sir, thank you very much. And especially thank you to our rector, Dr. Bhatti, for giving us this opportunity and encouraging us to, take a step in this direction. Thank you very much, Ji. Thank you.
Thank you very much, all participants and our speaker guest. And now this is the end of our session. We will start our next session tomorrow, inshallah. Join us for tea outside the hall.